Hey everybody, Mr. Brooks here again. So we're going to cover section 4.2 today. This is the existence and uniqueness. So we have seen this before in chapters 2 and 3 when we were dealing with scalar linear equations and also nonlinear equations as well. But for this one, we need to talk about, okay, if we're working on a problem, how do we know that we are going to get a solution? Because that's important, because otherwise there's no point in actually working on these problems. So we want to be able to establish a relationship just like what we did in chapters 2 and 3 to figure out, okay, if I work this problem, am I going to get a solution? And also, is it a unique solution? So does it make sense in this particular problem? So here I did do a lot of writing before this just because as you can see, there is a lot to write here. I don't want you to look at my back the whole entire time. So consider the IVP. So we have a system of linear equations going on here. Again, they're differential equations. And so here we have n of them. So just to see the format of them, we have P11. So it's not P11 in that case. It's P11, P12, P1n, and so forth. The reason that I wrote those that way is because later on when we write these in matrix form, which we're going to talk about it here in a second, but I am jumping ahead to kind of give you the emphasis of what we're doing. So these guys are going to make up the elements of that matrix, and so I wanted to show you where those are going to be fitting in, and this is why we're writing in that format. Also, these are all functions of t, so P11 and so forth, the Y1, Y2, all the way up to Y sub n, and the G1 through G sub n are also functions of t as well. So here again, the one represents the row, the other one represents the column that it is in this matrix. All right, and this is an initial value problem. So you see these weird symbols coming up, and so we have a lot of subscripts going on here, and you'll notice that we have superscripts on the Y1s, the Y2s, and so forth. So this is our initial value problem. So this is what we would have in general. These guys are our IVP part. So this is our initial values for some value of t. So t sub 0 we have seen before. And so this is our first function, whatever we have defined as our solution. When we evaluate it, t sub 0 is y1 sub 0. So the big thing I want to get out of the way is don't be freaked out by when you're seeing all these superscripts and subscripts all of a sudden popping out. It's just the nature of how things are. And so it's just a nice bookkeeping to have, so then that way we can represent this a different way when we get there. So all these guys are constant values specified at some point t sub 0. So this is a constant, that's a constant, that's a constant, so forth. Okay, so again, to ease your mind, these are just constant values that are popping up. All right, the next thing I wanted to emphasize here is these p's of I of j. That's just these guys. These are functions of t, okay? And g sub I, well, we've seen that one before. These are these guys here, the g1, g2, and g sub n, and so forth. All right, these are functions that are given to us, defined on some interval a, b as well. So everything's defined on a, b. It could be from a negative infinity to infinity, or some subset of that as well, or sub-interval, if you will. So again, this is just a generalized version of what our IVPs will look at. We'll see an example of one here in a little bit for that part. The nice thing is we can refer back to this IVP in a matrix form. But when we get there, notice I have tried, and this is going to be the hard part of me writing up on the board, that these letters here, the Y prime, the P, the Y, and the G, these guys are bolded. And if you look at your book, they use a bold font, which is a lot easier to see. And typically you won't see as much of a curl to the Y. You'll probably see the stick, instead of having like a script Y in there, you'll have a standard Y. Same thing with X when that pops up, and that will pop up later on in 4.4 and whatnot. These guys are talking about, they're represented by a matrix. So this is no longer talking about a scalar differential equation, though it looks like one. This is talking about those that are represented by matrices. And here, these are also matrices as well. All right, so now we're going to talk about, well, what do they look like in matrix format? Well, those are pretty easy for that. And this is again why I did the subscripts on here, and also why the book does that as well. It's again to show where these guys are going to be laying. So first of all, let's deal with that P of T right now, just because that's the big one that we have to deal with. All right, so we're going to bold this P as much as possible for that. All right, so this is our matrix. Again, I'm just going to write a subset of this representing the whole thing. So this is our P11, P12, so forth up to P sub 1n. So if we have an n number of linear equations that are popping up, we're going to have n number of rows and n number of columns. So this is going to be a square matrix, and we'll have n by n number of terms. So if this is a 2 by 2, we'll only have 4 terms. If it's a 3 by 3, now we have 9 terms. If it's a 4 by 4, 16 terms, and so on. So notice how things are going to be building up very quickly in a short amount of time. And that's actually going to cause an issue with us in Theorem 4.1 when we get there. All right, to continue our pattern, P12, this is P22, and so forth. So P2 sub n. And then we're going to continue this down to the nth row. So we're going to get P sub n1. And this is going to go out to P sub nn. All right. And I know it looks like capital letters, but they're typically, so when you're dealing with matrices, you typically have a capital letter to represent the matrix, especially a square matrix like this, and then lowercase to talk about the elements inside of there, the components of the matrix. So however way you want to write that, that's perfectly up to you, because one, we're going to get into specific problems here in just a little bit. All right, so that gets our P term. Our Y term is very simple. It's a column matrix or a columnar matrix, however you want to say that. Okay, so this is just our Y1, Y2 to Y sub n. And since we're sticking with those simple ones, G, notice that we only have a G1, G2, so forth. It follows that similar format. So bolded G of T is this G1, G2, so forth up to G sub n. All right, so that gets those pieces out of the way. And then our Y prime, we typically don't write it, but we can just to show that it is represented as a matrix as well. Again, bolding it as much as possible to help illustrate the idea that this is no longer talking about a scalar differential equation. So this is Y1 prime, Y2 prime, all the way up to Y sub n prime. And then we can also represent the reason I'm doing this as well is to show you how to represent this, talking about our initial value here. Okay. So Y1 sub 0, Y2 superscript 0, and so forth up to Y sub n to 0 as well. So this is representing everything that we have over here. So it is, sometimes it can be a cleaner format when writing this, but again, I wanted to show this so that way you have, one, how to write this in metric format, and two, we can represent these problems in multiple ways, so you need to be able to understand what this means versus what this means and how they're related to each other. All right, so Theorem 4.1 is the existence and uniqueness theorem. This is going to help us when we're talking about, well, do we have a particular solution that's going to happen, and can we guarantee its existence? And also, is it unique? That's a good name for a theorem. Let's write that down. So here, we're going to consider the initial value problem. And here, I'm going to kind of be lazy for a second just because of board space too. So consider the initial value problem. And here I'm going to show our matrix format. This is why this is important to help us with these. It'd be awesome if there was a copy and paste on a board, because this would make this a lot easier to deal with. But that's the lovely thing about this. And also recording yourself at the same time while saying that too. All right. So you still get my goofy personality in this particular example. All right, and then we have our initial values here. Y sub t sub 0 is equal to this y sub 0. Again, these are multiple values for this represented here. All right, and I'm actually going to reference that as well. So where y of t, p of t, g of t, and y sub t of 0 are defined by the matrices above. Okay, so again, referencing to these guys up here. All right, so the nice thing about this is now we need to talk about, okay, so we've considered our IVP, so we know what it looks like. It could go into either format, but this is what we want to see eventually for everybody writing. So what are our conditions? So again, with theorems, we have these hypotheses that we have to satisfy in order to apply the conclusion of it. So with this one, just like the existence and uniqueness theorems of the past, we are going to talk about the same exact thing, except you're going to notice something that's slightly different for this. All right, so here's our hypothesis part. So this is what needs to happen. Let our p sub I of j of t and g sub I of t, okay, where are these coming from? Well, this p sub I of j, that almost looks like a w. So let me fix that just a little bit. All right. These guys are the elements in here. All right. And the G sub I are all the elements in that one. Okay. So let those guys, every single one of those, this is the kicker here, be continuous on the interval AB. Containing, this is the important part, all right, t sub 0. Okay, so obviously we need to talk about, if we're talking about guaranteeing or the existence or uniqueness of something, we need to, again, talk about our IVP, and we have that interval around it. Otherwise, this doesn't make sense. But notice that in the past, it was pretty easy. We have a couple functions, we check them, we're good. This one, we're talking about every single function, p sub I of j and g sub I. These guys have to be continuous on that interval. So notice that the level of intricacy or difficulty, for that matter, or tediousness, if you want to talk about it, that bumps up by a lot. Okay, so and we'll talk about that as we go through the next example. So I'll save you for that one for just a second. So once we have that this is satisfied, this is the only conditions that we need, and I say only with a heavy heart. These guys have to be continuous. All right. So once those are continuous, this is the cool part. We can guarantee the existence of a unique solution. All right. Then the IVP has a unique solution on the interval AB. All right. That's the cool part. So once you satisfy that continuous idea that you have continuity on some interval, then you can guarantee the existence of a unique solution on that interval. That's the cool part. The hard part is talking about, okay, we need to show that these are continuous. And so we're going to go over an example here in just a second. All right. So I'm going to step back for a second and let you write this down because this is a lot of information. So I'm going to stop for a second and then I'll erase here. And I'm going to leave theorem 4.1 so we can reference back to it here in just a second. All right. So moving on. I know you all got that copied down. You didn't take a screenshot. Y'all are good students writing everything down, right? All right, so here is the IVP that we're going to deal with. So consider the following. So consider the IVP where we have y1 prime is equal to sine of 2t, and I'm going to put this in parentheses to help separate it from the rest of the problem because we want to be able to quickly identify it, so that's why I've got that there. Plus t over t squared minus 2t minus 8. Extend that out just a little bit more. y2 plus 4. Okay, so that's our first linear equation that we're dealing with. Our second one, y2 prime is equal to the natural log of the absolute value of t plus 1 times y1 plus e to the negative 2t y2 plus, and we'll make it a little bit interesting, secant of t. Okay, so again, these are our generalized, or this is if we were talking about a general solution. So now we want to talk about an IVP. So, and our IVP here is y1 of 1 is equal to 2, and y2 of 1 is equal to 0. Okay, so these are initial values that are going to occur. So again, notice that we have two functions that we're looking for. So, and we're going to have two initial values. So if we had 3, we'd have 3 initial values and whatnot. All right, so let's rewrite this. This is a big thing. So let's rewrite this in our format here. So solution, so SOL. So that is not what it typically stands for a lot of people. So this stands for solution, if you missed that before. All right, so no negative connotations unless you want to put it that way. All right, so our format that we want, again, is y prime of t is equal to p of t, y of t, plus g of t. All right, so our p of t is going to look like this format. So let's go ahead and get this one knocked out of the way. So sine of 2t, and then let's multiply the y2 here, and be careful. Okay, I'm not saying I'm going to mix this up, but in case there's an example in the book or something that you're working on, if it says y1, make sure it goes in the first slot. If it says y2, second spot. So just make sure that you have the appropriate ones going there. Some people like to rewrite having negative signs in the middle and positive out in front. But in these situations, I'm going to try to keep it like this format, so don't worry about that part. All right, so t over t squared minus 2t minus 8. And then we're going to have the natural log of the absolute value of t plus 1. So there's some nice things that happen with this one. And e to the negative 2t. So this is our p of t. Our g of t, this guy, is equal to, all right, notice what functions do not have a y with them. It's this 4 and this secant, okay? We have y1 prime and we have this 4 here, so that means our g1 is 4, and then our other guy is secant of t. So that's the easy way to spot what your g of t's are. They don't have a y attached to them, okay? So this is how we write those parts. And again, just for kicks, I'll write our initial conditions here to show you what this looks like, because at some point I could give you, okay, this is our p of t, this is our g of t, this is our y sub 1. Talk about its existence and uniqueness, and I don't give you this, okay? So be careful and be able to represent these in one fashion or the other, because you'll see both when they pop up. All right, so my question to you is, I want to find the largest interval which guarantees the existence of a solution, a unique solution, containing the t value of 1. Okay, so keep that in mind. We need t is equal to 1. All right. So I'm going to go ahead and erase this theorem. So again, determine, so this is our question. So I kind of jumped ahead a little bit, but this is the true question that I want. Determine the largest interval that guarantees the existence of a unique solution containing t is equal to 1. So keep that in mind, that t is equal to 1. All right. So going back to theorem 4.1, the one I just erased here, we have to guarantee the existence of a unique solution. So our hypothesis was that the p sub I of j and the g sub i's, these guys have to be continuous on that same interval that we're looking at, okay? So notice how complex this can be. So with a two-system problem, or two-equation problem here, we have 6 equations or 6 functions that we have to look at to talk about and guarantee their continuity on an interval. Well, think about that. If I bump this up to just a 3 equation system, we will then have 9 terms here, or 9 functions to deal with, and 3 more here. So we'd have a total of 12 functions that we'd have to look at to talk about their continuity. And a 4x4, well, then we have 20 that we'd have to deal with. So notice that this blows up really quickly when we're talking about these. So again, existence and uniqueness, we're going to talk about smaller systems just because, one, we're having to deal with a lot of functions to get there. Okay, you can do it. You're physically able to do it, and I guarantee that you guys are able to do it. So that's the awesome thing, is I know you guys are capable. It's just I'm not going to do that to you. We're going to stick with 2s and 3s for this part. Okay, all right. So since we're dealing with that, we need to look at these particular functions: the sine of 2t, this rational function, the natural log, the exponential, and these 2 guys here. Okay, well, let's look at these. We want to knock out the quick ones ahead of time so we don't have to worry about that part. All right, so let's look at these guys. Sine of t. We know, all right, so sine of t, where's that guy continuous? Take a second. Yeah, he's continuous everywhere. There's no value of t in here that's going to mess us up. Likewise, this exponential function, e to the power of negative 2t, that guy's good too. So those guys are continuous everywhere. Well, that knocks out our P matrix, so let's look at G. Well, secant's a different story, so let's get into 4. Well, 4 is a constant value. 4 is continuous everywhere. All right, so we know, and here, just so that way you're used to talking about what we're referencing with the generalized form. So this is P11 equals sine of 2t. P22, which is equal to e to the negative 2t. And G, since we only have one column here, all right, G1 is equal to 4. We know that these guys are continuous. Everywhere. Well, why did I go for these guys first? Well, it's because they're not going to mess anything up. They're the ones that are out there enjoying their time, just like you guys are, sleeping in. Me too. All right, so these are not going to be messing things up. It's going to be these functions here that are causing us issues. So let's get the easy guys knocked out first so we can focus on the harder ones. All right, let's deal with that rational function. Just go ahead and knock it off since we're knocking off this level already. So that's going to be P12, which is t over t squared minus 2t minus 8. All right, let's talk about where this guy is discontinuous. That's a little bit easier question in this sense. All right, well, he's only discontinuous when we have division by 0. So let's find out when the denominator, this t squared minus 2t minus 8, is 0. Well, in order to do that, let's just factor it down. So with the factors of negative 8, when added together, give us negative 2. Well, since I have a negative and a negative, that means the larger of the two is going to be negative. So we're going to get t minus 4 and t plus 2. So this guy is discontinuous at t is equal to 4 and negative 2. Okay? So discontinuous, just two places, everywhere else is fine. All right? Let's look at the natural log. This guy, we thought it's going to be hard, but there's a nice thing that's happening with this natural log here. All right? Natural log, where is it undefined at? Well, take a second. Yeah, it's undefined at negative values and at 0. Okay, the nice thing here is we have a built-in absolute value here. So that means this is never going to be negative on the inside, so we don't have to worry about that part. The only issue that we have with this particular function is that we can get 0. And in fact, the only place that we can get 0 is this value of -1. Okay? All right? Everywhere else is perfectly fine. That's great. I love functions like that. All right, secant. This guy's going to be the pain in the butt. So G2, secant of t. But it's not going to be too bad. Let's focus here. Well, secant is 1 over cosine. So the only issues we have is when cosine is 0. Well, cosine of 0 is discontinuous at odd multiples. Well, secant is discontinuous at odd multiples of pi halves. And the negatives of those as well. All right. So, well, that's a lot of information. This is divvying up that infinite interval from negative infinity to infinity, but I don't need to focus on that, okay? We're given an initial value problem. So I only need to talk about my value of interest, which is 1. So here, the only values I need to talk about that are around 1 is negative pi halves and pi halves. So take a lot of stress off yourself and be like, man, it's discontinuous here and here and here and here and here. Well, we only have to talk about where we want to guarantee a solution to occur, which is containing this point 1. All right, well, negative pi halves and t is equal to pi halves. All right, to help us out, I'm going to give an approximation. Well, pi is 3.14 divided by 2, so that's 1.5 and some change. All right. I already had that wrote down. Don't worry. I did not memorize that. I am that big of a nerd. I memorized it now. So here we're going to have negative 1.571 and 1.571 is the positive. So those are the only values close to 1. We don't have to worry about any values more negative than that or more positive than that. So that's all we're interested in. All right. So now applying theorem 4.1. So we need to talk about continuity. All right. We need to talk about continuity around the point of t is equal to 1. The nice thing here is there's no discontinuities at t is equal to 1, so there's no big issue there. Now we need to start talking about, well, what's the largest interval that we can take? Well, let's go big or go home. So the most negative we can go is -2. All right, actually technically it's negative infinity, but we're going to go to -2, be a little bit more reasonable than that. But if we do that, and so this is our value to the left of 1, okay? If I do that, that's going to include -1 and negative pi halves. So that's not a good choice. That includes 2 discontinuities automatically on the left-hand side of 1. So the next step is, okay, well, if I choose -1.57, that means I'm also including -1. So that means the furthest I can go away from the left-hand side of 1 is -1. So we can at least put that as our left-hand side. Now let's talk about the right-hand side. Okay, again, go big or go home. 4. All right, 4 is the largest that we've got there for discontinuities. However, that includes pi halves. All right, so the furthest that we should go out, or the only, the furthest distance that we can go out is pi halves here in order to apply theorem 4.1. So, by theorem 4.1, and since you guys are at home and you're going to have a take-home test for this, yeah, I'm going to ask you to put what theorem you're using here, because I want you to go back and understand what are we talking about here. So and these guys are not bad. So by theorem 4.1, the largest interval containing Now you can write this a little bit differently. I'm just finessing this as we go, so I could make it a little bit cleaner statement here in just a second. But the largest interval containing t is equal to 1 that guarantees the existence of a unique solution is -1 to pi halves. And that's it. That's all we have to do for this particular problem. So that's where we're going to stop this video at. So this is just part 1. We're probably going to have 2 more parts up here just to get through another example. And then the cool thing is with this chapter 2, we can rewrite scalar equations, you know, these big guys that we dealt with in chapter 3. We can actually rewrite those as a system of first order differential equations, which is really cool because there's some nice things that you can apply to this as we learn from the next couple sections like 4.4, 5, and 6. And so, all right, so that's it for today. All right, hey everybody, this is Mr. Brooks again. So I wanted to go over another quick example. This is going to be a short segment. Then we get into part 3 of the video, which is talking about rewriting, what I talked about finishing with part 1 video. So again, we're going to consider a linear system. Here is 3 differential equations, first order differential equations that we're dealing with here. The only thing I want to show for this particular video is show that u, which is equal to e to the t times this column matrix here, 0, -2, 1, and u, and v is equal to e to the 2t times 1, 1, 0. I want to show that these guys are solutions. So what I want to first do is, since these guys are in matrix format, I want to rewrite this as a matrix format as well. So again, y1 of t, or sorry, y prime of t is equal to p of t, y of t, all right, plus g of t. Again, I'm going to try to bold these letters to show that we're talking about matrix or matrices being represented in this particular equation. All right, so that's as bold as I'm going to put it. All right, so let's write this out. Well, notice here we have no g of t. That's the cool part about this one. So this would be considered homogeneous in that sense. All right, so let's write our p of t. So p of t is equal to, so this is the one to be careful about. Remember I said there could be things that are missing as well. So we have our y1, y2, and y3. Look at the coefficients of those guys. So the nice thing is notice that there's no weird functions there that we have to do. It's all constants. So this is 1, 1, and 2. All right. Then we have y2 and y3, but there's no y1, so we're going to represent it by 0, 2, and then 2. And then we have -1, 1, and 3. All right. And again, our y of t is represented as y1, y2, and y3. All right, the reason I'm doing this one, and I'm going to go ahead and show g, so then that way we can see how it's represented. So nothing exciting there. All right, so the reason I'm doing this is because I want to show you how to approach these problems, especially I know I'm going to give you some homework problems with this, talking about just show that these guys are solutions. All right, so first of all, what that means is when I throw these values into this particular system, I'm going to get out the derivative, okay? That's what it's saying here. So this is why writing in this format is more beneficial, because notice here we get to write it, and what we typically see here is when I throw in a function, multiply by some value, I'm going to get the derivative of whatever that solution was. So that means when we're looking at this, when I show this, u of t is actually equal to, now I'm going to multiply this in, 0, -2e to the t, and then e to the t on the bottom. And v, and the reason I'm writing this is because there's a next step that I'm going to show here, so I would stagger these as well. So e to the 2t, e to the 2t, and 0. All right? So what I want to do is when I throw these into for function of y, because these are my solutions, that's going to go into for y, all right, I'm going to get out their derivative. Well, what's the derivative of these? Well, this is where 4.1 was so important, is when we talked about the derivative, we could take the derivative of every single, the derivative of this matrix is the derivative of every single individual component or element in the matrix. So, when we take the derivative, I'm going to get 0, negative 2e to the t, and e to the t. So nothing exciting there. And v prime, this one's a little bit more exciting. We get 2e to the 2t, 2e to the 2t, and 0. All right, so we want that to happen. All right, so how do we do that? Well, if it's been a while for matrix multiplication and stuff like that, this is why I'm throwing this video in here, because this is to get you back on track with things. All right, so this is our check that I want to do to see if this is happening. So in our case, I want u prime of t to equal p of t times u of t, meaning when I multiply that matrix of 0, negative 2e to the t, e to the t, I'm going to get out its derivative when I multiply by this guy. All right, so when I do that, I get 1, 1, 2, 0, 2, 2, negative 1, 1, 3. Multiplying it by this matrix here of 0, negative 2e to the t, e to the t. And now I'm ready to rock and roll. The nice thing here is we are going to get one column here with 3 rows for that. So this is how matrix multiplication works. So we're going to take this row and multiply it by this column. That will be the first element in here. If we had multiple columns, we'd have to do this multiple times. So since we have a 3 by 1 and a 3 by 3, we are going to get a 3 by 1 back out of this. So if it has been a while, matrix multiplication only can happen if these two terms agree, and then the outside, the 1 and 3, that's what the matrix we're going to get in here. So if you've never been told that, now you will know. That's not going to be large enough. But if you already did know that, then this was not a waste of time, but just a reminder. All right, so again, row times column. Well, we have 1 times 0, so I'm going to do it for this first one here, plus 1 times negative 2e to the t, and then plus 2 times e to the t. All right, we're going to simplify this here in a little bit. Right now, I'm going to leave it alone. Then now the second row times the column. So 0 times 0. Then we're going to have 2 times negative 2e to the t, plus 2 times e to the t. And then our last one, negative 1 times 0, plus 1 times negative 2e to the 2, and then 3 times e to the t. All right? So when we simplify this, we want u prime to occur. All right, so I'm going to get 0 here. I'm going to get negative 2e to the t plus 2e to the t. Well, look what happens. We get 0 out of that. That's great. We're on board. That's exactly what we wanted. All right, so notice here, I'm going to get 2 times negative 2. That's negative 4e to the t plus 2e to the t. That leaves me negative 2e to the t. All right, last one. Hopefully we get this right. And we should. All right, unless I did something completely wrong. So I'm going to get negative 1 times 0, which is 0. Negative 2e to the t plus 3e to the t, leaving me positive e to the t. So yes, this one is equal to u prime. So that's our first check mark. All right. So, and I wanted to put a question mark there to show that this was true. All right, the next one. So this one I'm not going to write it out here. I'm going to simplify out as we go, but this way you already have a good example of what to go by. All right, so I want v prime of t is equal to, if this is true, P of t times V of t. All right, so again, I have my matrix 1, 1, 2, 0, 2, 2, negative 1, 1, 3. And we're going to multiply it by this column here of e to the 2t, e to the 2t, and 0. And what I want out of it is to eventually get 2e to the 2t, 2t, 2e to the 2t, and 0. All right? I'll go ahead and write out the steps. So we're going to get e to the 2t plus e to the 2t plus 2 times 0, which is 0. Then we're going to get 0 times e to the 2t, 2 times e to the 2t, plus 2 times 0. So that means we're going to get 0 plus 2e to the 2t plus 0. And then on the bottom, we're going to get negative e to the 2t plus e to the 2t plus 3 times 0, which is 0. And notice what happens. We get 2e to the 2t, we get 2 of those. So we get 2e to the 2t, 2e to the 2t, and these two terms cancel, leaving us at 0 on the bottom. And this is equal to v prime. So that's it for this particular example. But again, I wanted to show you that this is how you go about finding out if it's a solution. So this is a lot different. There are similarities because we wanted to have a function times our particular solution in order for this to work, to get the derivative out. And this time now we're dealing with matrices, and so this is the process to go by. All right, so that's it for this video, and we'll see you for part 3, which is how to rewrite higher order differential equations as a system of first order differential equations. Hey everybody, Mr. Brooks here again. So this is the third part of this lecture, and this is the last one we'll be doing today. So I actually am going to give you 3 examples for this rewrite. So this particular part of the section is really interesting because we can actually rewrite these higher order differential equations that we have seen in chapter 3 and rewrite those as a system of linear equations, which, yes, we don't know how to solve those guys yet, which that's what 4.4, 4.5, and so on is going to help us with. But the cool thing is once we have those tools down, we can take any higher order differential equation, provided that it's linear. So again, this is the big piece that it's linear, and rewrite it as a first order system, which is really cool. All right, so the reason that if we put scalar there is to talk about the differential equations we talked about in chapter 1, 2, and 3. Those are what we call scalar linear differential equations. And so then that way we have a reference system going on here. So when we're talking about first order linear systems, we're talking about the matrices that we're dealing with. So multiple equations. Here, scalar is talking about an individual differential equation for that part. Okay, so that's where that nomenclature is coming from. So I wanted to talk about that for real quick. So we can rewrite these guys as a first order system, which is really, really cool. And so this can take very complicated functions or differential equations and rewrite it as a system of linear equations. Okay, so there is a big benefit to this. So I figured the best way to go about this is show you a few examples of how to rewrite these guys. So the very first thing that we're going to deal with is this particular example here. We have a third order linear differential equation. So y triple prime minus e to the t y prime plus plus 3y is equal to sine of 2t. Okay, the very first thing that we're going to do is rewrite this. And actually, sorry, this was a second order. So make sure to make that correction. This is a second order differential equation. So I'm making it a lot easier because we only have 2 initial values for here. I should have checked that, but now I've got that. So again, make sure that you're dealing with a second order. So this is y double prime minus e to the t, y prime plus 3y is equal to sine of t. So the very first thing that we're going to do is rewrite this. So step 1 is do a rewrite as y double prime is equal to. So that's easy. So move everything over to the right-hand side. So notice this starts looking like those setups that we had in the previous lecture. All right. So we're going to get e to the t y prime minus 3y plus sine of 2t. So that's the very first step. It's very easy. Next, we're going to change the variables. So step 2, so this was rewrite. So now we're going to change the variables. Okay, because notice that we don't have a y1, y2, y3. So that's what we're going to do. So in order to change the variables, what we're going to do is first, we're going to define y as y1. So y of t is going to equal y1 of t. And the next thing that we're going to do is say y prime of t is equal to y2 of t. Okay? So that's all we're doing for that part. That would mean, when we rewrite this, this becomes y double prime is equal to e to the t y prime, which is now y2, minus 3y1 plus sine of 2t. Okay? So that's our first step. And now, we just rewrite it as an equivalent linear system. Okay? So that's our next step. This is the harder step. So the first two steps are pretty easy. Rewrite and then change variable. This is all we have to do. The next step is write an equivalent linear system. So notice that we only have one equation. That's the kicker there. But the nice thing is we do have some other elements in here that are going to help us out. So the first thing that we're going to do is, again, the system that we're going to be looking at. That's too big. Again, I'm going to try to bold this because we're writing this now representing a matrix. Y prime of t is equal to p of t y plus g of t. All right. So we want to get it that way. So let's define a couple of things. Well, I'm going to be using y1 and y2. So y1 and y2. Those are my two functions that I'm going to be looking at, my two solutions eventually. So now writing the derivative piece, okay? Y prime of t is equal to the derivative of y1 prime and y2 prime. Okay, so this is where we get into representing this. Well, the derivative, let's think about that for a second. The derivative of y prime or y1 is y2, isn't it? Because we stated that y1 prime, and I am going to write this out as we go so we can see it working. This is equal to the derivative of y of t. Right? We stated at the beginning, right here, when we did our change of variables. So we said y of t is equal to y1 prime. Well, we just took the derivative of this. All right? Well, y1 prime is the same thing as y prime, which is y2. Okay? And so y of 2t. And y prime here, well, that is the derivative of the derivative, right? Because we just said that y2 of t is equal to y prime. That was our change. So that means that's y double prime of t. And we just stated with a rewrite that we did here and here, specifically this one because we want it in terms of y1 and y2, is e to the t y2 minus 3y1 plus sine of 2t. Well, another way to write this, just that way we're simplifying this down. Again, I'm just rewriting here. Okay. This becomes y2 negative 3y1 plus e to the t y2 plus sine of 2t. Notice that it looks like that system that we're looking for. All right, the next step, again, with this rewrite is to talk about, well, this was an initial value problem, okay? Y sub 0. Okay, throwing in those values, well, that means this is y of 1 of 0, and this is y2 of 0. Okay, well, think about this. Well, what was y of 1? Well, y of 1 is equal to y of t. Y of t, y of 0 is equal to 2. All right, and I'm going to write that here in a second. And y prime, well, y2 is y prime, okay? So this is y prime of 0, which is equal to 2 and negative 1, respectively. All right, so notice here that we have now rewrote our initial conditions, our IVP, as the following matrix of 2, negative 1, and 0. All right, so now we're ready to move on and rewrite this thing. Making sure I got this right. So, well, I need my P of t. All right, well, P of t is equal to what's in front of y1 and y2. All right, well, notice there's no y1 in this first system of linear equations. So this first linear equation here, so we get a 0, and we have a 1 in front of the y2. And then next we have negative 3y1, so negative 3, and e to the t. So that's our P of t. All right, and now our G of t. Okay, well, G of t is those functions not associated with y. So notice that there's a 0 here, but then we have sine of 2t. And there we have it. So this is our representation. So this is our P of t, this is our G of t, and this is our y of t. So we've already got all of our pieces. So, so now we have, and I'm going to rewrite this, that way we can see it instead of all scattered out here. So the first order system that represents our original IVP is y prime of t is equal to P of t, y of t plus G of t, y of t sub 0 is equal to y sub 0. All right. Defined by the following matrices. P of t is equal to the matrix of 0, 1, 3, e to the t. G of t is equal to 0 and sine of 2t. And y of 0 is equal to the matrix 2, negative 1. And this is our solution. All right, so that is how you represent these guys. So again, step 1 is a rewrite of the system. So we take the highest order, keep it on the left-hand side, move everything over to the right-hand side. Step 2 is we change a variable. So we start y of t, then we go y1, y prime is y2, y double prime, y3, y triple prime, y4, and so forth. So we continue that rewrite. Then we expand it out, or we rewrite it in matrix format. So our y of t, that's always going to be the case, is y1 all the way through y7. Then we write our relationships. So y1 prime was equal to the derivative, which was y2. y2 was equal to our equation. So if this had been a third order, we would have had y prime of 3, which would have equaled the original. This would have equaled y3. So that's how the rewrite works. So typically you will start seeing a lot of zeros for the top part, and then you have your equation at the bottom. And then rewriting your IVP part, your initial values, is very simple. What does y1 and y2 represent? Well, it represented y of t and y prime of t. At 0, these were 2 and -1. And then taking this, getting the coefficients out with all of those that involve y and those that do not involve y. That's our g of t. All right. So let's go through a couple more of these to get used to that. So I'll give you a second to write this down. Take a screenshot of it if you have to. And then we'll get into our next equation here. All right. So now that we have that idea, let's go through these next couple of problems. So I'm going to give a second for you to rewrite, and then we'll go on from there. Again, each time I write a example up, if you want to go ahead and pause the video for that particular example, pause it and then work on it on your own, and then start it when you've either hit a spot or you got it done and you're like, yeah, I want to see what this guy is. So let's bump up the difficulty here. So y triple prime. So this is a third order that we're going to deal with. So I want to make sure I write this correctly. T squared y double prime plus 3t y prime plus 5y is equal to e to the -4t with initial values of y sub 0 is equal to 1, y prime of 0 is equal to 3, and y double prime, my apologies, is equal to 7. Okay? So the very first thing that we're going to do in this situation is, again, step 1 is rewrite. So I'm going to move everything else over to the right-hand side, keep y triple prime by itself. All right? So we get t squared y double prime minus 3t y prime minus 5y plus e to the -4t. So this is probably your easiest step out of all the steps. Step 2, change variable. Okay, well, y of t is equal to y1. Y prime of t is equal to y2. Y double prime of t is equal to y3. So that means when we rewrite this, we're going to get y triple prime is equal to t squared y3 minus 3t y2 minus 5 y1 plus e to the -4t. All right? So right now, step 2 should look like this. Okay, and I'm just double checking on my paper here too. All right. So the next step is step 3 is rewrite everything as a system. Okay, so my y of t is very straightforward. This is just y1, y2, and y3. Okay, so when I do that, let's look at y prime. Okay, so I'm going to come over here to give myself some more room. So y prime of t is equal to, and again, I'm going to go through that step-by-step process to show. So I get y1 prime, y2 prime, and y3 prime. So again, when we're dealing with a system of linear equations, this is kind of what it looks like at the beginning. So these primes look like ones. course, that's kind of hard to tell with my handwriting. All right. Well, we just stated that y1 prime, all right, so y1 was equal to y of t. Well, that means y1 prime is equal to y prime, which is y2. All right. Well, y2 prime, well, that's y prime prime, which is y3. Okay. And the next one, y3 prime, y sub 3 prime is equal to the derivative of the second derivative, which is the third derivative, which is this t squared y sub 3 minus 3t y sub 2 minus 5 y1 plus e to the negative 4t. So this is my system. Okay, so if I dropped the dropped this sign here and dropped the matrix symbols around this, that would look like a system of linear equations, just like what we would deal previously. So focus on that part. So now to rewrite it in that format. Okay. I'm going to put linear system here again because that's what we're talking about here. So our first order linear system, okay? So we need y prime of t is equal to p of t y of t plus g of t, okay? So with that, p of t, just focus on everything that has, just like before, so nothing's changed on that part, just focus on everything that has a y in front of it, okay? So we don't have a y1 and we don't have a y3, but we do have a y2 by itself, so 0, 1, 0. Likewise, we don't have as y1 and y2 on this one, so we have 0, 0, 1. So that's going to be about the normal. I'm not going to say it's 100% of the time, but that's the typical normal for this. And then here, this is where I said be careful of a couple videos ago, because I want you to make sure that you pay attention to what's in front of each of your y1s, y2s, and y3s. Our y1 is over here. It has a negative 5 in front of it, so it's negative 5 here. y2 has negative 3t, and y3 just has a t squared. Okay? And now our g of t. All right, well, g of t is equal to everything that's associated or not associated with y, so there's not one in the first equation or the second equation, but there is this e to the negative 4t here. So that's our two pieces for that part, okay? The next step is rewriting our initial values. And they were also at 0 as well. All right, so our initial values of y1, y2, and y3 is y prime, and y double prime. So this is 1, 3, 7. All right. And that's our first order linear system. All right. So if I were to rewrite this in a slightly different format to show you, again, this is what I would like to see, but this is another one that I would also like to see because this is a little bit cleaner looking, is another way to write this. And it still has the matrix form. Is you write your p of t 0, 1, 0, 0, 0, 1, negative 5, negative 3t, and t squared, multiplied by y1, y2, y3. So that's, notice here that that's exactly what we want. So we have row times column, so we're going to get zeros for these guys times y2, so that gives our y2. Zeros for these guys, we get a y3, and then minus 5, y1, minus 3, y2, and t squared, y3, plus g of t, which is this 0, 0, e to the negative 4t. So that's another way that we could represent. All right, so that's all I have for you today. That, again, was just to go over 2 quick examples for this. There is a third if you'd like to see it. Just let me know in the discussions for this, and I'll either post it or at least do a write-up of that. All right, y'all have a wonderful day.